There is a version of the future where the sky slowly goes dark, not because the stars burn out, but because space itself carries them away faster than their light can ever reach you. First, the distant galaxies vanish, then the nearby ones. Then, in the final hours, the very same force that emptied the sky reaches down into your own solar system and pulls the planets off their orbits. Then, it pulls the Earth apart. Then, your body. And finally, in the last fraction of the last second, it reaches inside the atoms you are made of and tears them open too. Physicists call it the Big Rip. And unlike almost every other way the universe could end, this one comes with a countdown. Whether it happens at all depends on a single number, a number we have measured, but not precisely enough to know our fate. So let's find out what that number is and what happens if it points the wrong way. The story starts in 1998 with the discovery that genuinely shocked the people who made it. For most of the 20th century, one thing seemed certain. Ever since Hubble showed, in 1929, that distant galaxies are flying away from us, we've known the universe is expanding. And everyone assumed the expansion had to be slowing down, braked by the collective gravity of everything in the cosmos. The only question was how much. Two rival teams set out to measure that slowdown, using Type Ia supernovae, exploding stars that all detonate at almost exactly the same brightness, which makes them perfect cosmic measuring sticks. Measure how bright one looks, and you know how far away it is. Measure enough of them, and you can reconstruct the entire expansion history of the universe. Both teams expected to see the universe breaking. Instead, the supernovae came back too dim, too far away for any slowing universe to place them. They checked and rechecked each half, hoping the other was wrong. They weren't. The expansion is not slowing down, it is speeding up. Something is pushing everything apart and getting stronger at it. That discovery won the 2011 Nobel Prize, and it forced cosmologists to add something enormous and invisible to their equations, an energy woven into empty space itself, pushing outward against gravity. They called it dark energy. And today, it makes up about 68% of everything in the universe. More than 2/3 of all there is a thing we cannot see and do not understand. Here is where the story turns on a knife's edge. Dark energy is described by one crucial quantity, which physicists call W, the ratio between its pressure and its density. And the entire far future of the cosmos hangs on it. If W equals exactly -1, dark energy is a cosmological constant. Its strength never changes. Every cubic meter of space always carries the same amount. The universe expands faster and faster, but structures survive, galaxies stay bound, stars keep their planets, atoms stay whole. The universe ends slowly, in a cold, silent freeze, the heat death. But if W is even slightly below -1, -1W01, any amount at all, then dark energy becomes something far stranger. Physicists call it phantom energy. And it has a property that sounds impossible. Its density increases as space expands. Normal matter thins out as the universe grows. Phantom energy does the opposite. More space means more phantom energy, which pushes space to expand faster, which creates even more phantom energy. A runaway feedback loop built into the fabric of reality, accelerating without limit. In 2003, physicist Robert Caldwell and his colleagues followed that runaway to its conclusion and gave the resulting apocalypse its name. Their paper was titled, "With Unusual Bluntness, Phantom Energy and Cosmic Doomsday," because if W is less than -1, the doomsday isn't just possible, it's scheduled. And that is what makes the Big Rip unlike any other ending. It has a schedule, a countdown running in reverse, each stage arriving faster than the last, cascading from the largest scales down to the smallest. Suppose the rip arrives in roughly 20 billion years. Here is how the end unfolds. About 1 billion years before the end, the accelerating expansion overpowers the gravity binding the largest structures in the universe, the great galaxy clusters. They begin to dissolve, their members scattering into the dark. About 60 million years before the end, the expansion overpowers the gravity holding individual galaxies together. The Milky Way, our own galaxy, begins to come apart. Its billions of stars drift away from one another, and the familiar band of light that has arched across every human night sky simply unravels. About 3 months before the end, the force reaches into individual solar systems. Planets are peeled away from their stars and flung into the void, orbits stable for billions of years unbound in a matter of weeks. 30 minutes before the end, planets themselves come apart, not shattered by impact, simply unbound, as the space inside them expands faster than rock and iron can hold together, a world dissolving from within. And then, in the final fraction of a second, the expansion overwhelms the electromagnetic force that holds atoms together. Atoms are torn open, then their nuclei, and in the very last instant, space-time itself reaches an infinite rate of expansion, and the universe stops being a place where anything at all can exist. Here's the strangest detail. An observer would see almost none of it coming, because each stage happens so much faster than the one before. Billions of years of quiet emptying, then months, then minutes, then an instant. The whole catastrophe compressing into a blur right at the finish. The universe looks calm, and calm, and calm, and calm, and then everything comes apart at once. Everything depends on that one number, W. So what have we measured? Our best answer combines the Planck satellite's map of the cosmic microwave background with surveys of supernovae and galaxies. And W comes out very close to -1, give or take a few percent. That is exactly the problem. -1, give or take a few percent, straddles the boundary. The measurements are perfectly consistent with a safe cosmological constant and a slow heat death. And they are also consistent with a value just below -1, phantom energy, and a big rip. The error bars cover both futures. We are standing at a fork in the cosmic road, and we cannot yet read the sign. And recently, the picture got more interesting. Results from the DESI survey, mapping tens of millions of galaxies to trace dark energy across cosmic time, have hinted that dark energy might not be constant at all, that its strength may be changing. If that holds up, the comfortable picture of a fixed constant is wrong, and the question of where W is really heading becomes very much alive again. Now let me be clear about the science. Those hints are not confirmed. Most current analyses still lean toward a value at or just above -1, which would mean no big rip. And even where a rip is possible, it lies tens of billions of years away, far beyond the death of our own sun. But probably not, and not for a very long time, is a very different sentence from no. The number that decides between an eternal freeze and a violent tearing apart of reality. We have measured it, but we cannot yet read its final, crucial decimal places. Our fate is written in a digit we haven't resolved. There is something almost intimate about the Big Rip compared to the other ways the universe could end. The heat death is the universe slowly forgetting itself over unimaginable spans of time. Vacuum decay is deletion at the speed of light, arriving without warning. Both are impersonal, they happen to the universe as a whole. But the Big Rip is different. It ends the universe by working its way inward, from galaxy clusters, down through galaxies, down through solar systems and planets, and finally into the atom itself. It undoes the smallest, most stubborn bonds in all of existence, the ones that hold you together. In the Big Rip, the final victims of the universe are not distant galaxies or dying stars. The very same atoms forged in the hearts of dying stars that survived the entire violent history of the cosmos to briefly assemble themselves into a living, thinking person, undone in the last instant by the same expansion that once spread them across the sky. And the whole verdict, a quiet drifting cold or a final tearing apart, hangs on the third decimal place of a single measured number. We live in a universe where the difference between two completely different eternities is thinner than a rounding error. That is not a reason for fear. It is a reason for humility and wonder, and a genuine reason to keep measuring. Step back, because something quietly astonishing is hiding in this whole story. And it isn't the Doomsday, it's this. A species of primate on a single small planet, having had telescopes for only about 400 years, can now look out at the universe and calculate, from the brightness of exploding stars billions of light years away, not just how the cosmos began, but the range of ways it might end, and roughly when. We have taken the question, how does everything end? A question every human culture has asked, and answered only with myth, and turned it into a measurement, into a number with error bars, into something we can, in principle, pin down. That the number happens to sit on a knife's edge, unresolved, is almost poetic. The universe is refusing, for now, to tell us whether it will fade or tear. but not because the question is unanswerable, only because we haven't measured carefully enough yet. And yet is the most hopeful word in all of science. Whatever the answer turns out to be, it lies tens of billions of years away, long after the death of the sun, long after the entire remaining story of life on Earth. Nothing in this video will ever touch you, but you get to know about it. You get to hold in your mind the possible endings of the entire universe. And that, a temporary arrangement of atoms, understanding the fate of all atoms, may be the most improbable and beautiful thing the cosmos has produced. But suppose the number is safe. Suppose W is exactly -1 and nothing is ever torn apart. What waits at the end of that road is, in its own quiet way, no less final. A universe that slowly outlives everything within it, drifting into a cold and endless dark. That's the heat death. And it's another echo waiting right here. Subscribe and listen to the dark with us.